in statistics, we have parametric statistics and we have non-parametric statistics. In parametric statistics, we have many assumptions, and parametric statistics perform better than non-parametric statistics. Example, so we have what they call Mann-Whitney. Okay, we have what they call Kruskal-Wallis, and we also have what they call one-way ANOVA. Both of them are used to do the same thing. The only difference is that Kruskal-Wallis is for non-parametric, while one-way ANOVA is for parametric. Now, one-way ANOVA performs better than Kruskal-Wallis, but just that one-way ANOVA has more assumptions than Kruskal-Wallis. Now, one-way ANOVA will only perform better than Kruskal-Wallis if all the assumptions of one-way ANOVA are satisfied. So in a situation when one of the assumptions is violated, it's not proper to use one-way ANOVA. Then we have to fall down to Kruskal-Wallis, even though one-way ANOVA would have been better. But in this case, you can no longer use one-way ANOVA because why? One of the assumptions was not satisfied. So I'm trying to tell you that in statistics, when you're talking about parametric statistics, we have assumptions. So you have to know all the assumptions for a particular method. Then you have to test for the assumptions. If they have 5 assumptions, the data satisfy 4 and phase 1, you can't use that method. It passed 4, but failed. You just use it as your WAEC. Even though you get A's, but you fail chemistry, you can't continue. You have to repeat WAEC. So that's how it is. So even if it satisfies 8, but fails 1, you can't continue. You have to look for another method, or you then fall down to the non-parametric equivalent to it. Now, we have Mann-Whitney U-test. Is the equivalence of the t-test. That is a parametric statistics. Mann-Whitney U-test is a non-parametric statistics. So look at what non-parametric here. Look at them. So one sample. This is the one non-parametric one sample is the equivalent method to one sample t-test. We also have independent sample is equivalent to the independent t-test. What's the difference? This is a parametric statistic. This is a non-parametric statistic. We know that this is more powerful. The power of this is greater than the power of this. That means in a situation when the assumptions are satisfied, if you use this, it will give you accurate results more than when you use this. But when one of the assumptions are not satisfied, you can no longer use the parametric. Take note of that. It's very important. So how do I know a good statistician or a good analyst? Once I see your work and you don't test for the assumptions, I know that you don't even know statistics, because it's like the bedrock. You don't know what you're doing. In as much as sometimes I do analysis for people and I don't test for assumptions. Maybe I just want to get my money, which is bad. And most times it's because not that I just want to get my money, because that's what they want. They just don't want something complex. They just want only the result. They don't want to test if the result is correct or not. They just want to have figures. And me, I just want money. I do for them. I try to tell them that you have to test for the assumption because that's the proper way. But they say they don't want it. They don't want to start explaining too many things on the day of their defense. But that is wrong. So how do you know a good analyst? A good analyst first must check if the data is appropriate to be used for that particular method. So if I want to work on regression, I will check if the data I have is appropriate to be used for the linear regression. I'm trying to emphasize this because it's very important. So like I said, we're supposed to treat either one-way ANOVA or linear regression, but we can't treat this without talking about the assumptions, because that's what you do before you start doing any analysis. You test it. So now let me list a few of these assumptions. We have what they call normality. We have what they call outlier. We have multicollinearity. We have autocorrelation. and we have homoskedasticity. Another name for homoskedasticity is constant variance. Another name for constant variance is no heteroskedasticity. No heteroskedasticity. Let me say it again. So I mentioned outlier, I mentioned normality, I mentioned multicollinearity, I mentioned autocorrelation, I mentioned constant variance, and I told you another name for constant variance is what? Homoskedasticity or no heteroskedasticity. So, okay. So now I will start to explain each of them so we understand what they mean. When we talk about outlier, so let me start with that outlier. When we talk about outlier means, is there an extreme value in your data? If there is an extreme value in your data, any result from that data will not be accurate. Now, let me explain. Sometimes we tell, maybe after marking results, we go to the class and tell the student that the performance of this class is poor. That doesn't mean all the students failed. That doesn't mean, okay, there may be just one particular student. Okay, let me not use this let me not use this particular example. Let me use another one. So let's say if I have, let's say in a class, students are getting 1, 2, 1, 2, 1, 2, 1, 2, and just one student scores 10/10. Now, that particular student will increase the mean. When I want to calculate the mean, that particular student will increase the mean of the class. So maybe the mean of the class may be up to 3. And if you are reporting that the mean of this class is 3, that's not a true representation of that particular population. Because why? Most of the students, we are getting 1. Very few got 2. But because of that student that got 10/10, the student will increase the mean. And the student will make us to report a value that is not really a true representation of the population. So that's what I'm trying to. So that's an outlier. So what we mean by outliers, they are extreme values. They are not following the pattern within a data set. They are not following a pattern within a data set. They have extreme values. If others are getting 8/10, 9/10, 10/10, 8/10, 9/10, 10/10, and a student got 0, just one student. That student that got 0 will make the mean of the class to drop to 7 or 8 or 7 or 6 because of why it got 0. And that's when you report 6, that's not a true representation because most students got 8, 9, 10. So outliers affect the result. So first, when you want to do an analysis, you check if, depending on the analysis, some requires that, or most analysis require that. You check if there's an outlier. Then we have different ways of treating the problem of outliers. That's not what I'm teaching you. But one of the ways is to delete that particular cell. So for example, let's say this one is an outlier. One of the ways is to delete this. Just delete it. That student that is not a true representation of the population, you can just take him out of the class and do the analysis with the remaining ones. But this is not the only way of solving the problem of outliers. There are other ways. So I've explained outlier. So let me explain the next one, normality. Normality is simple. We test that the errors of the model follows a normal distribution. The errors of the model follows a normal distribution. Now we want the errors to follow a normal distribution. If it doesn't follow a normal distribution, there's a problem. What do we use to test it? We use, I remember I skipped this, we use the PP plot to test it. In normality also, sometimes we test if the variable follow a normal distribution. So not only the error, sometimes we test if the variable follow a normal. So we can test if this follows a normal distribution. And if I want to do that, I go to descriptive, I go to p plot. We call it the normal probability plot. Normal probability plot. I want to check student scores, so I move it to here. Okay. Okay, let me show you something that I was too fast. Are we seeing normal? So we are testing for normality. So this is it. It's still plotting, still processing. So let me just show you how do we interpret this normal probability plot. If this, let me open Minitab. When testing for normality, I prefer using Minitab. And I've already explained why. I will also explain. Now, if we said it follows a normal distribution, if most of these points are on this line, there's a diagonal line. You can see the diagonal line. So if most of these points are on the diagonal line, we say it has satisfied the normality assumption. If most of the points are what on the diagonal line. One thing why I don't really use SPSS for normality tests. Graphical method is subject to or depends on viewer's perspective. It depends on what you are seeing. Santos can look at this and say most of the points are on the diagonal line. Emmanuel can look at it and say, no, now look at this. All these places are not on the diagonal, they are far from the diagonal line. So two people can look at a plot and come out with two different conclusions. So that's why I don't really enjoy making a decision with that is for PT plot with SPSS, because it doesn't give me p-value. I prefer using p-value. So one of the ways I do this, I take my data to Minitab. Are we seeing what I'm doing? I take my data to Minitab and I go to normality test. Remember in SPSS, it's called what? PP plot. Yeah, it's called normality test, which is still the same thing. You move your data, C1. Then it will give you the opportunity to choose, apart from the graphical method, which other test do you want to use? So we have Anderson-Darling. Anderson-Darling is a normality test. We have a Ryan Joyner, say is similar to Shapiro-Wick, is also a normality test. We have Komogorov, Smirnov. You use anyone. Most times I use this Anderson-Darling. Sometimes I use this. So if you want title to show, you click OK. So this is the plot. This is the plot. Why is the plot different? Let me see. Did I copy the right data? 72 instead of 72. Let me see. It's supposed to be 1000. Okay. So let me see the graph again. Is 0 to 1, 0 to 40. One of them is standardized. Let me see. Analyze PP plot. Normal. Normal. Okay. Normal probability plot of student score. Can't really say why the two graphs look different. Okay, but that's all. I don't know why they are looking different. They're not supposed to be different. But one thing I discovered here is that this is using the actual value. So maybe that's the difference between SPSS and Minitab. This one is using the standardized value. Are we seeing here it's from 0 to 1? So it's standardized value. Standardized value. Why this is using the actual value? The actual value, you see, we have up to 78. Why this is using standardized value? So that's the difference. But this is the reason why I prefer using Minitab, is because of the p-value. This is the reason. It gives me p-value. So using this p-value, I can make my decision. The null hypothesis. Now I discovered that people have been they used to have issues with null hypothesis, alternative hypothesis. Always know what is the null hypothesis and know what is the alternative hypothesis, so you don't make any mistake. Now for each test, there is the null hypothesis for it and the alternative hypothesis for it. Take note for, I've told you for chi-square, the null hypothesis is no association. That's for chi-square test for association. The null hypothesis is no association. Why the alternative is there's an association. So always take note of that and use it always for chi-square test. For t-test, the null hypothesis is that if we are talking about two variables, variable 1 is equal to variable 2, there is no significant difference. Always, that is the null hypothesis. Always. Is the alternative hypothesis that you will say it is greater than, or it is less than, or it is not equal to. Always take note of that. Now, for normality test, back to this, the null hypothesis is always there. It follows a normal distribution. The null hypothesis is that it follows a normal distribution. Why the alternative hypothesis is that it doesn't follow a normal distribution. So looking at this, like I said, this can be based on personal judgment, which I don't like doing. Looking at this, the p-value is telling us that it doesn't follow a normal distribution. Of a truth, from this point to this point, they are all aligned on the diagonal line. They are all aligned on the diagonal line. But this point and this point, they are not aligned. And this test is telling me that this point, these points, and this point, they are significant enough to make it to fall outside of normality. That means they are not normally distributed. Are we seeing how important it is? It's telling me they are not normal. So that's why p-value is very important. Now we can say this is an outlier. So let me check if it's an outlier. Let me check. So I can come to start. Okay, let me use outlier test. Graph. So let me click OK. I don't know this plot. Let me go to Minitab. Okay, it gave us a statistic. There's something it gave us. I saw something. I don't know if this is a p-value. That means if you want to learn about this, I've not used it before. Like this thing can give you different results. If you want to learn about it, I think it's p-value. So you read about drops test, but I think this is p-value. Why I think it's p-value? Because this is it. We have level of significance. So it means the p-value is 1. So read about this. Okay, look at null hypothesis. All data values come from the same normal population. Okay, no, this is the normality test we did. Okay, no, this is for normality. All data values come from the same normal distribution. Okay, then the alternative is that they have an outlier. So the null hypothesis is no outlier. The alternative is that there is an outlier. So the p-value is 1 point. So that means we are not rejecting. Since we are not rejecting, it means no outlier. So that's what he's trying to tell us, no outlier. So we can confirm this using our box plot. Box plot, we go to graph, charts. We use box plots. We use this. We're talking about student scores. Okay. So no outlier. The assignment I gave to you guys, when you did for chemistry, you saw some point outside this box plot. So if there's, for example, there was a point here. If there was a point here, there was a point here outside this line. There was a point there. We say there's an outlier. So because there is no point, it means all the points are between this to this. So there is no point outside it. That means there is no outlier. And this is also confirmed by the group test. You see one thing about guys, Minitab sometimes will tell you the null hypothesis. So Minitab told us the null hypothesis. So this statement here means no outlier. Why this statement means there's an outlier. And the p-value is 1.00. So we are not rejecting, it means no outlier. So that's why I say personal judgment can deceive you. It means looking at this plot, someone may conclude that there's an outlier, but it's based on the p-value. It's telling us that there's no outlier. So I've been able to explain outlier and normality test. Outlier and normality test. Please give me a minute. Wait, I'm coming. Stop sharing. Let me pause this. Okay, so sorry for that. So we are back to this. So I've been able to explain. Chidera, are you still with us? Emmanuel, are you still with us?
Sure.
Okay. Thank you. So I've been able to explain what we mean by outlier and normality. So the next thing I will explain is multicollinearity. Multicollinearity. So I also explained what we can use to test for outlier. So I've shown you how to test for outlier using Minitab. Minitab uses Grob's test. Like I told you, I've not used it before, and I don't think I will still use it. I prefer using a box plot, but that doesn't mean you can't use. And I use Malanobis distance. If I'm talking about maneuver, I use Malanobis distance. But you can use box plots, you can use Malanobis distance, you can use Grob's test. This is the first time I'm seeing this. I've not used it before. So your choice. Like I said, analysis doesn't have a particular pattern. Box plot. Okay. So the box plot also shows that there is no outlier. I've told you how to. The point can be here, the point can be here, or the point can be here down here. For it to be above this line, it will be below this line. I think there is an outlier. To be above this line, and to be above this line and below this line. So the box plot, what I use mostly is the box plot. So I've shown you how to also use Grob's test if you want. And I've explained what we mean by outlier, extreme values. So now let me explain multicollinearity. Now, when we talk about multicollinearity, we are talking about variables having a strong correlation among themselves. Variables having strong correlation. Now, when two variables have a strong correlation, it means they are saying the same thing. And if they are saying the same thing, why use both of them in the analysis? Using both of them in the analysis means just like English. What do they call if you are speaking when you want to use two similar words, using it together? Is it tautology they call it or what? So that's what we are saying. So if two things in statistics, two variables are saying the same thing, why use them in that particular analysis? So when you use them, you get a problem called what? Multicollinearity problem. So in an analysis, most analysis, or depending on the analysis, we don't want multicollinearity. That means all the variables you are going to consider should be saying different things. That means if you want to come to Futo, one variable should tell you come through Iagua. The other one should tell you how to come through Obinze. Another one should tell you how to come through Ezobudo. So these three variables now, they are saying different things, all pointing to how to come to what? Iagua. So that's how it is. So when two variables are saying the same thing, you don't use them. Let me think of an example. So let's say I want to work with a regression problem. The dependent variable, the variable of interest is the size of my house. The size of my house. I can say the size of my house depends on my salary. And I can say the size of my house depends on what else can I use now? Depends on the okay, I can't think of any now. Size of my house depends on my salary, and the size of my house depends on let's say the state I live in. So now if there is a relationship between the state I live in and the salary, let's say we know that maybe in Lagos State they will pay you more than in Imo State. I'm assuming now that in some states they pay more than some states. So in that case, you discover that there will be a relationship between states, but those state is not a continuous variable. But I believe you guys have understood what I'm trying to explain. If two variables are saying the same thing, I can't really think of a real life variable. So if two variables are saying the same thing, and you do their correlation analysis, they have a strong correlation. It means they are saying the same thing. You can't use them. Using them will lead to multicollinearity problem. Now, we have different ways to test for multicollinearity. Different ways to test for multicollinearity. One of the ways is using the correlation coefficient. Now, if the correlation coefficient is close to 1 or -1, we say there is multicollinearity. If the correlation coefficient is close to 1 or -1, we say there is multicollinearity. Another way to test for it is using the variance inflation factor. Variance inflation factor. Now, this will be taught in final year for those in photo, but you don't need to wait till final year for you to know it. It's not even proper. Why should you wait for when they've started teaching you regression? So even before, like I told you, before you do any regression analysis, you're supposed to test if the assumptions are satisfied. So you doing regression without testing for the assumption is wrong. So that's why I'm saying this is, yeah, they will teach you in school, but knowing it now is not bad, because if you want to do analysis for someone or regression that they've taught you, you have to first test for the assumption, because if you don't do that, you are committing an error as an analyst. So you have to take note of all this. So for multicollinearity means the variables have what strong correlation amongst themselves. Ways of testing it: correlation coefficients, variance inflation factor. Now, what this variance inflation factor, if the number is close to, okay, let me do something. If the number is variance inflation factor, if the number, what is that number itself? Okay, let me do the analysis. Let me see. Plus 5. Okay, let me just do, okay, let me do another variable. Calculate C3 plus 15. Okay, so let me do regression analysis. So I will explain this multicollinearity very well. Option. I'm not teaching you guys regression now. I just want to show you something. Graph. So this is normality. Storage. Okay. So this is what I mean by variance inflation factor. Variance inflation factor. So I see the VIF. So that's what I mean. So it must not be greater than 10. If it is greater than 10, that means there is multicollinearity. If it is greater than 10, there is multicollinearity. On that, this is the variance inflation factor. Another way to test for it is using correlation coefficient. Correlation coefficient. So I can do for 2 of them. Okay. Look at the correlation coefficient. So another way to test for it is using correlation coefficient. This is how to do it in SPSS. You test using correlation coefficient. So chemistry course. So look at the correlation coefficient here is low. So it shows that there's no multicollinearity. So something like this. So if we are using correlation coefficient, how do you know if there's multicollinearity? The value should, if the correlation coefficient is close to 1 or -1, most times I judge from maybe 0.85 to 1 or -0.85 to -1. So if it is within that range, I can conclude that there is multicollinearity. Sometimes, but most times I use variance inflation factor. So variance inflation factor is simple. It should not be more than 10. We also have a condition number, condition index, but let's just focus on 2 for now: correlation coefficient and variance inflation factor. They also have tolerance. If you want to use tolerance to judge the tolerance, if the tolerance is close to 0, it means there's multicollinearity. So let's not learn too many things. Let's focus on VIF and correlation coefficient. So I've been able to explain 3 assumptions. Now, forget all these things I'm explaining. Not that I don't forget it, but it may look complex, but it's very simple. When I start doing a complete analysis, you will understand what I'm saying. So, okay, let me show you an analysis I did so that you understand a few things I've explained. Okay, analysis. Let me see analysis on regression. Regression. So this is a test for autocorrelation. So you must do the assumption before you do the analysis. So test for multicollinearity. So look at the VIF. The VIF method was used for testing for multicollinearity. The VIF of the two independent variables are given in table 4.2. There is little or no multicollinearity in the data set since all the VIFs of the independent variables in table 4.2 are less than what? 10. Very simple. That's what I've been trying to say. So when you do the analysis, you don't need to, you're not learning any formula. You just use your point and click method to get the value of VIF. If it is less than 10, you know that there is little or no multicollinearity. It means you can go on. This is for Malanobis distance. Okay, I use Malanobis distance to test for outlier. Like I told you, you can also use box plots. And today we learned, I just for the first time I'm seeing it, we can use Group's test. But I don't think I will still use it. So I will keep on using my Malanobis distance or box plot. Then this for normality. The normal probability plot is used to test for normality. The errors are normally distributed if most of the points are aligned on the diagonal line. So I told you that this method is based on what you are seeing and may be different. I can look at it and say it's normal. Another person may look at it and say it's not normal. So I like using Minitab because Minitab will give me the p-value. So when it gives me the p-value, I know that if it gives us the p-value, all of us will say the same thing. So the normal probability plot is given in this. So based on this, I concluded that this one is okay. This one you may not need Minitab because most of the points are already on the diagonal line. So the residuals are normally distributed since most of the points are on the diagonal line. Okay, now let me explain homo. So I've explained 3 now. So the next one I want to explain is homoskedasticity. Homoskedasticity. Today we will not do much. Maybe I will just explain. Okay, let's see how far we can go. I want us to understand the assumptions, very important, because we're going to use them in different tests. One will learn regression, one will learn ANOVA. One will learn MANOVA, even though MANOVA was not part of our course outline. But I think we may consider it, but it's not part. We may consider it. So when we start doing all these things, we need all these assumptions. So that's why we have to take our time to understand them. So the next thing I want to explain now is homoskedasticity. Like I said earlier, another name for it is constant variance. Another name for it is constant variance or no heteroskedasticity. No heteroskedasticity. Now, what does it mean? It means when we talk about constant variance, we are talking about the variance of the error term is constant. Or we say there is no, okay, the variance of the error term is constant. So what are the ways we can, one of the ways we can use to test for homoskedasticity? The only method I use is the graphical method. That's the only method. They have other ways to test for it. But since I've been doing analysis, I only use the graphical method. Now, how do you make your conclusion using the graphical method? First, you check if there's a systematic pattern. If there's a systematic pattern. Now, looking at this normal plot, there's a pattern. What's the pattern? They are moving on the diagonal line. There's a pattern. Look at the pattern, a straight line. There's a pattern. If the thing is, look at what I want to do now. If it's moving like this, there is also a pattern. If it is moving like this, that's a pattern. If it is moving like this, it's a pattern. If it is moving like this, it's also a pattern. So what I mean, so if for you to say there is homoskedasticity, it means the values must be scattered, There must not be, like, look at it now, you can't say there's a pattern. This one is scattered. So that's how, so when it is scattered, it means there is homoskedasticity. Now, what do you plot? You plot the residual against the predicted value. You plot the residual against the predicted value. So look at what I mean. So if you want to do analysis, you go to analyze, you go to regression, you go to linear, but you come to plots. If you want to test for homoscedasticity, it will ask you for y. Remember I said y is what? Residual. Y is residual, which is this resid. No, this predict, this residual. Y is residual. Look at what you plot. You plot, take note of this, maybe you can write it down. You plot residual against predicted. Residual against predicted. So go and write that one down. So residual, then you come to predicted for x. Remember, we are working with z. Z predict. Then you click. If you this for normal probability plot. So normal probability plot, you don't need to select what you want. Just click this, it will come up. So let me just put variable, yeah. Normal for is there any number, yeah. Maybe SN. I say this one is normally distributed. Most of the points are on it. Almost all the points are on the diagonal line, normally distributed. I wish that there is no pattern, it's scattered. Remember, look at what I mean by pattern. If it's moving like this, there is a pattern. If it is moving like this, all of them are moving like this, there's a pattern. If all of them are moving like this, just look at my cursor, there's a pattern. But in this case, it's scattered. You can't identify a particular pattern. You can't say it's bell shape. You can't say it's horizontal. You can't say it's diagonal. So there is no pattern in this. So in this case, we say what? Homoscedasticity. That means there is constant variance. That means there is no heteroscedasticity. Very simple. What do we mean by homoscedasticity? The variance of the error term is constant. We want the variance of the error term to be constant, because in a situation when the variance of the error term is not constant, we get wrong results. Our result from that analysis will not be accurate. So that's why we want the variance of the error term to be constant. Any question? Do you have any question?
No, sir.
Okay, please.
So I wanted to ask, but
okay,
since
ask,
I didn't follow up now.
Ask. Yeah, ask.
I don't know. Is this a different topic from what you've been teaching before I came?
No, this is a new topic entirely. We've not thought. Okay, Chidra, you have many questions. Okay, Lois, this is a new topic. I've not taught anything on this before. This is the first time we're treating it.
Okay. If I watched the video from the beginning.
But if you still have any question, ask. It will also make me to re-explain what I've explained. But I think you have to listen to the first part. Chidera, you said you have too many questions. Chidera,
the grammar is too much. You have to in the questions. There are much anyway, but we'll see what to
okay, you want to type it or you will say it? Which of them? Which one do you prefer?
I will later type them.
Okay, you want to type? Okay, type. Just let me know once you finish typing. So I will answer them. It's good to ask questions, because as you ask questions, you get to understand it more. Okay, so let's continue. Or please be typing your question. Let me pause the. I want to let me attend to this lady. Type your question now, please. Okay, so we can continue. So Lois, let me give you a brief explanation again of what we are doing. In one of the trainings, I said there's what we call assumptions in statistics. Now, it's just like you cannot write jump if you cannot write for UTM if you don't pass jump. That's how it is. So if you don't pass jump, you can't write for UTM. So now, before you can do regression, before you can do ANOVA, before you can do MANOVA, before you can do most of these analysis we are going to learn from henceforth, you are supposed to, the data is supposed to satisfy the assumptions for that method. Now, if the data doesn't satisfy all the assumptions for that method, you cannot do the analysis. You can't. If you try to do it, you will get wrong result. I remember anything about statistics is for decision making. We are trying to make decisions. So that's anything about statistics. You are trying to make decisions. So if the data you are using to make decisions is giving you wrong results, you end up committing a big mistake because you give wrong conclusion also and wrong decision. So that's why we must use the right method, the right tool for the analysis. So for you to use the right method and right tool, you must always ensure that that data satisfies all the assumptions. Like I said earlier, if we have 6 assumptions and the data satisfies 5 and fails 1, you can't continue. You must look for another method to use. You can't do that analysis, even though it passed 5. So I've explained what we mean by outlier. Outlier means extreme values. How do we test for outlier? Box plot. So like I said, all these things you understand better when I do a practical example. But I just want everyone to have a knowledge of what they mean. The normality means the data follows a normal distribution. In statistics, we have different distributions. We have binomial, we have chi-square, we have exponential. So, but we are saying in normality that the errors follows a normal distribution. In some tests, we talk about the variables. The variables we want it to follow a normal distribution. If it doesn't follow a normal distribution, it will be skewed. But that's not what we are learning. Then I've explained what we mean by multicollinearity. For multicollinearity, we say two things should not be saying the same thing. I've tried to use photo as an example. If they say explain ways to come to photo, you can come through Nekede, you can come through Binze, you can come through Eziobodo. Now, I've tried to use 3 ways to come to photo, and the 3 ways are saying totally different things. Now, if you discover that you are doing an analysis and 2 of the variables are saying the same thing, it's no longer proper to use that 2 variables. What do you do? Maybe you drop one of them, choose one of them and use and leave the other one because both of them are saying the same thing. If you are playing a football match and your wingers, they are playing the same way, the same pattern, the same skill, it's not proper to use both of them, because if you use both of them, they will know your opponent will know how to mark them, and you can't operate well. So what you do is you use one that plays style A and use another one that plays style B, so that when you combine style A and style B, you'll be able to defeat your opponent. So that's what we are trying to say. Why use 2 variables that are saying the same thing? No difference. You're repeating the same thing, which is not proper. So we drop one and continue. So that's what we mean by multicollinearity. The variables must not, the statistical way of saying it is that the variables must not be highly correlated. And I said we use VIF and correlation coefficient to test for it. We have other ways to test for it, but we'll stop at that. Then for VIF, we don't want it to be more than 10. You are not calculating anything. SPSS will give you all the results. Just know how to make your conclusion. Then we've talked about homoscedasticity, and I said we are going to use the graphical method. What are we plotting? We're plotting residual against predicted, and I've shown you how to do it. You come to analyze, if you're using SPSS. When you're example, I want to do regression. I will teach you how to do regression before you come to plot. You plot residual against predicted, residual against predicted. Then when the plot comes out, that is the homoscedasticity plot. Homoscedasticity plot. Then how do you make a conclusion? There should be no pattern. There should be no pattern. When there is a pattern, there is a problem. So the last one we are going to explain is autocorrelation. Autocorrelation. Now, this is not, when I say the last one, I'm not saying that's the last assumptions in statistics. What I'm listing is the major assumptions. Now, when we start treating each method, I will tell you for this particular method, these are the assumptions. For regression, these are the assumptions. For ANOVA, these are the assumptions. But now what I'm trying to give you a brief summary of all of the major assumptions in statistics. Not that, so we still have other ones. We have we have other ones. When we talk about logistic regression, logistic regression has its own assumption. So we're going to treat that one when we are talking about logistic regression. So now we are talking about the major assumptions. So the last major assumption we're going to talk about is autocorrelation. Now, what do we mean by autocorrelation? When we're talking about autocorrelation, we're talking about serial correlation. What do we mean by serial correlation? We are saying that the error terms must not be correlated. The error term must not be correlated. Look at what I mean. Okay, let me do an analysis now. Regression, linear, then I'll click save the error. No, save the error. Are we seeing it? I'm not teaching you this now. I just want to show you something. Then if I come back to my SPSS, look at the error term. Now, these two the error terms must not be correlated, must not have any relationship. This must not have any relationship with this. This must not have a relationship with this. This should not have a relationship with this. This should not have a relationship with this. So that's what we mean by the error term must not be what correlated. Now, why we call it serial correlation? Why is different? In normal correlation, we talk about two variables, right? Why in serial correlation, we're talking about the values of a variable should not be correlated with each other. In this case, we're not talking about two variables. We are talking about only one, but the values in that variable should not be correlated with each other. That means your price, example, now the price of the price of rice today should not have anything to do with the price yesterday. The price of rice tomorrow should not have anything to do with the price today. So that's what I mean. The error term of this should not be related to this. This should not be related to this. So that's what we mean by autocorrelation. Now, what we are going to use to test for autocorrelation is Durbin-Watson. Durbin-Watson. Don't bother yourself cramming it. Don't like cramming the formula. What we are not teaching formula here. So example, now if you come to, I'm in Minitab now, regression, fit regression. If you click results, are you seeing Durbin-Watson? Durbin-Watson. Once I tick this and click OK, it will come out in my results. Look at it, okay, because I use the data I use is not proper. But this is where you will see the results, Durbin-Watson statistics. You will see the results there. You see it. So that's all you need. Once you know, see that result, you use it to make a decision. Now, how do you make your decision? We are going to work with a table. We are going to work with a table. So I will send a table to our WhatsApp group that we'll be using. Then even if you misplace the table, once this Durbin-Watson doesn't have p-value, Minitab or SPSS doesn't give us p-value. So that's how we work with the table. So you can always go to your Google and download Durbin-Watson table. So even if you are not with that table and you want to do analysis for someone, you can just go online and download Durbin-Watson table, then write PDF. You click any of them. So most times I like opening more than one before selecting. Okay, so look at it. I will see Durbin-Watson table. So you don't need to bother yourself. So this is it. So okay, I don't even need to send it. So all of you should go and download it yourself. So this is the table. So you saw how I did it. This is the table. Okay, so what I will do a complete analysis. Then I will show you how to use all this. But I just want us to understand. So I've been able to explain all the assumptions that we are going to use for this, the major assumptions we are going to use. Any question? Any question?
No, sir.
Chidera, I'm waiting for your question. No, it's funny, lady. I saw what you did.
Please, I'm sorry. I'm looking at rats.
Okay. No. So now let's do analysis for regression. So let me use this data. So I want to do analysis for regression. So when I finish this, we'll stop. I've already interpreted it, so I will just send this. That doesn't mean it's a perfect work. Sometimes I don't do perfect work for people. I just do work and collect my money. But it's not that I do a good work, though, but not really perfect sometimes. The dependent variable, yeah, I'm trying to look for dependent variable. So I will just interpret it, then send this. Use this to explain it. I will not write anything. Dependent variable GDP. Okay. So now this is a regression analysis. The dependent variable here is GDP. While the independent variables are rec and cap. Dependent variable. Now, when do we use the regression? We use the regression to study the relationship between variables. So if I want to study the relationship between variables, so I want to get a model. Okay, let me give an example. There was a day a man called me. He said he's a farmer. This is a real life application of regression. Like all these things we are learning now, they apply to real life. He called me that he's a farmer. He discovers that the quantity of fertilizer he uses, no, sorry, he discovered that the size of his yam, the yam he will harvest, depends on the fertilizer, the quantity of fertilizer he used. That's his own discovery. So he discovered that if he uses more fertilizer, the size of the yam would be bigger. So he was saying that, is it possible for him to get a model? So when he gets this model, he will just tell the model, if I use fertilizer of size of quantity 85, what is the expected weight? Lois, can you mute yourself? What is the expected weight of the yam I'm expecting? So this is practical application of regression. So he's trying to get an equation to study the relationship between what? Fertilizer and the size of the yam produce. So that he doesn't need to, he said, now for him to know the weight of the yam, he has to wait for the harvesting season before he will know the weight of the yam. So he said, is it possible that I can know the weight of the yam using my equation? Now, let me also explain what we mean by regression using another example. It's that there's what we call precision medicine. Though this is a higher, this is not just linear regression, this is a higher type of regression. But I just want to still explain what we mean by regression. Now, yes, we have different types of malaria drugs. We have different types of malaria drugs. So the three of them are working well. Now, they discovered that some drugs will work better for some set of people, while some drugs will not work, that same drug will not work better on another set of people. Maybe people that are fat, drug A will work better. But if they are slim, drug A will not work, drug B will work. Then drug B will not work well if they snore. So I will need to get a model. So when I get a model, a patient comes, I'll ask the patient, I will look at the patient. If the patient is fat, the patient does he snore? I will check the weight, the height of the patient, check the heartbeat, check the pulse. When I get all these things, I will put it into the model. Then the model will tell me, give the patient drug C or give the patient drug B. Now, this is a regression model. Now, what's the model doing? The model is trying to study the relationship between the type of drug and the weight, the heartbeat, the pulse of the patient. So when we're talking about regression, we're talking about what? Studying relationship between variables. And when we want to study relationship between variables, we have a dependent variable and we have one or more independent variables. We have one, okay, no. We can have more than one dependent variable. We can have more than one dependent variable. I'm defining regression generally now. We can have more than one dependent variable. But just know that we have a dependent variable and one or more independent variables in linear regression. So now what we are talking about now is linear regression. We have one dependent variable, one or more independent variables. Now, another name for independent variables is explanatory variables. Another name is predictory variables. Predictory variables. So we have explanatory, predictory, independent. Then for dependent variable, another name for it is response. Dependent variable, response variable, and explained, the explained variable. Explanatory is for independent, explained for dependent. Response is for dependent. Predictory is for independent. So I'll try to explain that. So now what the dependent variable here is GDP, I think so. The dependent variable here is GDP, yes. So we want to study the relationship between GDP and REC and CAP. So we want to check if recurrent expenditure, which is that's the meaning of REC, and capital expenditure, if I know both of them, can they help me to know the GDP of the country? That means if I come to Nigeria and ask Nigeria in 2020, Tell me what's your recurrent expenditure. They tell me. In 2020, tell me what's your capital expenditure. They tell me. With both of them, I should be able to predict or get an estimate of the GDP of Nigeria in 2020. That's the meaning of regression. You are trying to get an equation that will study the relationship between the independent and dependent variables. So we discover that this is the variable of interest, the dependent variable. I want to show that it depends on these two. So that's regression. You go to analyze regression, linear. Remember, I told you must test for the assumption first. So dependent variable will go, GDP will go to dependent. Why this will go to this? And remember, I told you you can use arrow or you use this. You click and drag. So I've entered my dependent and independent variables. You go to statistic. I want descriptive. I want Dobbin-Watson. Are we seeing Dobbin-Watson? What's Dobbin-Watson used for? Autocorrelation. Autocorrelation. Look at collinearity. Are we seeing multicollinearity? Collinearity. So this will give me VIF, collinearity. I'll click. So I've tested for two assumptions now. I'm telling SPSS, test for Dobbin-Watson, autocorrelation, test for collinearity, multicollinearity. Continue. I'll come to plot. I want to test for homoskedasticity. For you to test for homoskedasticity, what will you do? You put residual. Residual will be here against predicted. Predicted will be here. That's the third assumption I'm testing for now. This is the fourth one. To test for normality, I will test using normal probability plot. This is the fourth one. This normal probability plot, normality. This is homoskedasticity. This is multicollinearity. This is autocorrelation. You are not calculating anything yourself. Very simple. Continue. Then I'll click what? Option. Let me see if there's anything in option. There's nothing here. Okay, very simple. Let me cancel this and repeat this, so that we know that anything that will be in the output is my regression. Okay. I just want a fresh page in my output. That's why I canceled that. So this is your result. You copy your results to Word. So now let me interpret. I want to interpret now. Based on this, there is homoskedasticity. Based on this, there is what? Homoskedasticity. Based on this, there is homoskedasticity. Based on this, there is what? Normality. Why is you have to state your reason. The reason why there is homoskedasticity, yeah, there is no systematic pattern. I've explained what to mean by pattern. If all the points are moving on they have a pattern, we know when something has a pattern. Either it's moving in a cycle or moving zigzag, in circular form, or what do they call that? It's moving this way like this. That's a pattern. Or it's moving like this. That's a pattern. Are you seeing my cursor? So in this case now it is scattered. You can't tell me any particular pattern. So because there's no pattern, we say what? The homoskedasticity. I will show you this is the complete work I did, the analysis. So I will show you. I've interpreted two now. Remember, I told you have to interpret all the assumptions first before you start the main analysis. This is not the main analysis. The assumption is not the main analysis, but it's very important because without it, you can't do the regression analysis. So look at VIF. The VIF is 3.4, which is less than 10. The tolerance, okay, we're not using tolerance for this class. So VIF, which is less than 10, it means that there is no multicollinearity. There is no multicollinearity. Then the Dobbin-Watson. Dobbin-Watson, look at what you do in Dobbin-Watson. With Dobbin-Watson, look at what you do. In Dobbin-Watson, look at what you do. You go to your table. Let me check. Who is that? Mute yourself. So Dobbin-Watson. Let me show you where Dobbin-Watson is. Okay, look at Dobbin-Watson. Look at the decision rule, which I will send. I will maybe send it. I don't want to send this document so that people will not copy, so I will not send it. So look at so you are seeing it. So it's in the training. So you can get look at the rule we use. Let me explain this rule. So you go to your table. So you download your Dublin Watson table. So which is this? Look at this. Model, read this. I will say this. Model with what? An intercept. So it means you count the number of variables, including the intercept. So K means the number of variables. So how many independent variables do we have? Remember, you must add the intercept. That means number of independent variables plus 1. In this work we did, we have 2 independent variables. Remember, we have 2 independent variables. What are the independent variables? Cap and rec. The dependent variable is GDP. So we have 2 dependent variables. So you add 1 to it. So it becomes what? 3. You then come to K3. You ask yourself, what is the N? N for this work is 16. N is 16. So you come to your table, you check K3. We know why we are using K3. 2 independent variables plus 1, the intercept. Then you check 16. Look at 16. 16. So look at the 2 values you use. So my DL is 0.663. My DU is what? 1.447. Now you take note, you write these two numbers. Then this is how to interpret. Let me bring the output. Lois, I've seen your end. I'm coming. This is how to interpret now. The Dublin Watson. This value should not be less than this. If it is less than this, there is autocorrelation. We want this value to be greater than this. When it is greater than this, it means no autocorrelation. But if it is in between, we behave like Nigeria election. We say it is inconclusive. That means you can neither conclude that there is autocorrelation or say there is no autocorrelation. It's inconclusive. In as much as I don't like that, but if it is inconclusive, it will not. I don't stop doing my analysis. I continue. Remember, I told you that if it fails any assumption, you stop. But now I can't say it failed my assumption because I can only say it has failed my assumption when this value is less than this. That's when I will say it has failed my assumption. But we only say it has passed the assumption when this value is greater than this. But in this case, this value is not greater than this. So because it is not greater, it is in between. Whenever it is in between, we say it is inconclusive. So let me see what I did here. Hope I did the right thing. 1.253. That manipulation. 1.253. Model with an intercept. Okay, maybe I made a mistake. Let me see. Okay, no. Okay, look at this, please. Look at this. Look at the meaning of K. K means what? The number of regressor excluding the intercept. Okay, sorry for that. So if we're excluding the intercept, it means, and this is, it has entered the record, what I said earlier. So if we're excluding the intercept, it means our K is 2. That means you don't include intercept. So if we're not including intercept, it means we work with 16 and K2. We know why we are using K2. We are not including intercept, the number of independent variables. 16 K2. 16 K2 is what? So this is the variables we are using. So let's check our output again. Is this value greater than this? Yes. So because this value is greater than this, it means that what? There is no autocorrelation. No autocorrelation. Remember, I've taught you now, when we say it is inconclusive, it's when it is in between them. So look at what I interpreted here. Lois, I'm coming. I'll get back to you. Test for autocorrelation. Remember, I told you that when you want to interpret, you can state it like this. But if I want to do sometimes when I do analysis for people, I don't state it like this. I just write it in Word. What I will write is, to test for the autocorrelation assumption, we are going to use the Dublin Watson statistics. Full stop. Maybe then the Dublin Watson statistics will be used to test the null hypothesis that the residuals are not serially correlated against the alternative hypothesis that is residuals are serially correlated. We are going to use 0.01 level of significance for this test. And the decision rule is that we reject the null hypothesis if the Dublin-Watson statistic is less than the lower confidence limit of the Dublin-Watson tabulated value. We are not going to reject if the Dublin-Watson statistics, that I'm interpreting the second one now. I'm showing different ways of interpreting it. You can write it this way. Another way is writing it in words without stating H0, H1. You just write it in like a sentence. We do not reject the null hypothesis. This is called Dublin-Watson statistic. If the Dublin-Watson statistic is greater than the upper limit of the tabulated Dublin-Watson value of the tabulated Dublin-Watson table, then we say the result is inconclusive if the Dublin-Watson statistics is between the lower limit and the upper limit of the tabulated Dublin-Watson value. So I've been able to write it in words. You can write it like this also. Then you state your decision. So in this case, we are not rejecting H0. Since the what? We are not rejecting because the Dublin-Watson statistic is greater than what? The upper limit. So this is how to interpret for autocorrelation. Lois, you can ask your question.
Sir,
Yes.
on that Dublin-Watson table, the
Yes.
DL and DU, what does it mean?
Lower limit, upper limit.
Oh, okay, okay.
Mhm.
Okay,
So when it's between, this value is between both of them, we say it's what? Inconclusive. You can either reject or do not reject. But when it is less than this, there is autocorrelation, which is a problem. When it is greater than this, there is no autocorrelation, which is what we want. So I've taught you now how to interpret homoscedasticity, how to interpret normality, how to interpret multicollinearity, how to interpret autocorrelation. I'm not going to send this table. All of you saw how I downloaded this table. So if I send this table, I'm not teaching you the right thing. Okay, take note of this. So this is 1% too. Alpha level is 0.01. So they have another table for alpha level 0.05. Are we seeing? So this is 0.05. While the other one is what? 0.01. So you have to learn how to get tables yourself online. So if you look at what I did, I opened 3 and I selected the best. So you can, not that it's the best, you select the one you want. So this one is only for 0.05. This table is only for 0.05. It didn't give us option to use for 0.01. This one has 1%, 0.01. It has 0.025. It has 0.05. Maybe this is the best, but this one has for many. Okay. So you download the table, and I'm not going to also send this interpretation because if I send it, people will copy it. So I want you to interpret it in your own words. So back to this. So I've taught you how to explain this. So the only thing we've not tested for is outlier. So if you want to test for outlier, you can come to graph. You can use Malanobis distance, but I will not use it for this class. So we'll come to box plots, remove this, you check for cap. Oh, let me see if I can do the 3 at the same time. Let me see if I can do the 3 at the same time. Okay, I cannot. Okay, let me do that one after the other. So you move this. Okay. There's an outlier. Are we seeing this? There's an outlier. Move this. Click this. No outlier. We are learning. So I've done GDP. We've done for cap. So the remaining rec. There is no outlier. So what's the solution? Would this outlier is at what? Case 16. Case 16. So you come to case 16. Let me see. And it's for cap. Case 16 is case 16. It's from cap. Are we seeing that is an outlier? Are we seeing others are getting 3, 3, 3? The IS before was 1, 6. This one came to 2000. So it's an outlier and it's not giving a true representation of this data. So the option is you have different ways of treating outlier, of solving the problem of an outlier. Like I told you, it has failed one assumption, you can't continue. You can't continue. So you have to solve that problem. So what do you do? So maybe I can decide to delete this cell. That is how I want to treat it. And if you are doing this, it also has to be in the work. So as you are interpreting, well, after testing for outlier, you now tell them that because of the presence of an outlier, you are going to delete it. All these things you interpret, you are going to delete it. And you will repeat everything from the beginning. So I'll delete this cut. Then I will repeat all the analysis. So let me clear this. Let me clear it. I like clearing it before doing a new analysis. Regression, linear. So you test again. My VIF is 2.15. It has satisfied. Wow. It scattered this one. That means I have to go to Minitab to use Minitab to conclude because now it has scattered this one. This one is still okay. This one doesn't look okay. VIF is okay. Where is my Dublin Watson? 117. Let me see if my Dublin Watson is still okay. Let me see. But you know how to check it, so let's continue. But I've explained all I want to explain. So let me go back to, let me just show you this, then we'll end the class. So this is what I did for the guy. Descriptive statistics, like I told you, you have to give a detailed explanation. Like I was not serious with this work. Normally I told you I don't like keeping table like this. So this is how I arrange my table. Like I was not serious. It was an urgent work and the guy just needed it. Please, I want to leave. My battery is low. Okay. You can leave. We are ending the class soon. Yes, you can leave. You can leave. Thank you. So you put this. You're welcome. You put this. So this is how I arrange my table. Like I told you guys, this is how I arrange my table. It was an urgent work. Then you explain. I decided to give him a plot of this. I didn't change the color. You can change the color if you want. Remember, all these things will be done in SPSS. So you can't change color here. So I give him a plot of all the variables. Then I want to say, so the assumptions are we seen, I started linear regression. The assumption of the OLS model are tested to determine if the data are suitable for the OLS method. Like I told you, if it fails an assumption, you can't continue the analysis. So that we want to check for suitability of the data for that particular method. So test for autocorrelation. I told you can write it this way or you write it in words. You write it this way or you write it in words. So Dublin Watson, you state your null hypothesis, alternative hypothesis. The Dublin Watson table that you got from your analysis. This is the DL from your table. This is the DU from your table. Then you make your conclusion. Test for multicollinearity. How you get your VIF. So this is how I do it. You just create your table. Sometimes I just come here and double click. I will delete all these things first. How do I do? Or you create your own table. I just delete all this. That means I will repeat the analysis and copy this one for VIF. Maybe I can delete if I want to delete tolerance. I can do it like this and copy. Then I will repeat the analysis to get back that table again. I will repeat the analysis to get back the full table. So I can just come to this place and copy and move to Word. So that's how I got this table. Remember, I told you I don't arrange my table this way. So this was an urgent work. So that's why I give him like this. So there is little or no multicollinearity. Why? Because of what? The VIF, they are all less than 10. Then he tests for outlier. I use Malanobis distance. Malanobis distance told me there is no outlier. Bob's plot was telling us there's an outlier. So I use Malanobis distance. So test for normality. We saw that this one is normally distributed. Test for almost scarcity. Look at the normality plot is used to test for normality. The errors are normally distributed if most of the points are aligned on the diagonal line. So the residuals are normally distributed since most of the points are on the diagonal line. So test for almost scarcity. There is almost scarcity in the data since there is no systematic pattern in the plot of residual against the predicted value. So there is no pattern. So the data satisfy the assumption of OLS arrow model. So that's it. So we are going to stop here for today. I've not taught you how to interpret regression. I've not taught you how to interpret regression. Standard error for what? Standard error for what?
Hello, sir.
Yes, standard error for what?
Concerning the error, like you
Type.
deleted it
Type.
in that before you posted.
I can't hear you. Type. Which standard error? Are you talking about this standardized residual? Is that what you are calling standard error? Is it standard deviation or what? Which standard error? Tell me the standard error you are talking about. So we'll stop there for today.
Can you hear me?
It's breaking.
Sir,
Just type.
okay, can you hear me, sir?
It's breaking. So let's stop here for today. I'll answer your question later. We'll talk online. So I'm going to stop here for today. I've not explained how to interpret regression. I'll do that in our next class. So what I did basically today is to explain how to test for the assumptions of an analysis. So that's what I did basically today. So I'll give you an assignment and ask you to test for only the assumptions. So that's all I'll ask from you. So thank you for joining us today. So we can end the class.